So let's talk about the magnetic force on a current carrying conductor. Now, if a single particle feels a magnetic force when moving through a magnetic field, then a wire with a current moving through it must also feel a magnetic force. So here I have a wire, that's my orange line here, and I've got some box inside here where I'm going to place a magnetic field. Okay, so here I have my wire, and then I'm going to place a magnetic field in it into the board. So I'm going to make my X's into the board. Okay, now what's going to happen? Let's say that my current, let's see here, I've got my wire is going to be deflected to one side or the other depending on the direction of the current that's moving through it. So if I have my wire that has current that's running in this direction right here, okay, that means that my electron is going to be moving opposite the direction of the current. This is the direction of I down this way. My electron is going to be moving opposite the direction of current, so my thumb is going to be pointing back towards me. My fingers are into the board in the direction of the magnetic field, pointing down into the ground. And then not my palm, because that would be the direction of the magnetic force for a positive particle. For a negative charge for my electron, the direction of the magnetic force is going to be pointing out of the top of my hand here. And so the magnetic force is going to be pointing in this direction for this wire within this magnetic field, and that's going to deflect my wire toward this direction. Okay, and then we would see oppositely, if the current were running in this direction here, okay, if I was running in this direction, my fingers into the board, my thumb opposite the direction of the current, because that's the direction of the moving electron, and so then the top of my hand tells me the direction of the magnetic force, which is in this direction. Okay, so the moral of the story is that our wire can get deflected if there's a current moving through it and it's in a magnetic field. So what is this magnetic force on our current carrying wire? Well, we can write it like this. So we've got this force is going to be equal to the force on each charge carrier, which we already saw, QVB sine theta, where theta is our angle between the direction of current and our magnetic field in this case, okay? And then we multiply it by the total number of charge carriers. So we have to know the total number of those carriers per volume over some volume. So we've got the cross-sectional area of our wire A times the length of that wire L. Okay. So this is the magnetic force on our current carrying conductor. Now, if you remember, when we were talking about current, that the current is also equal to our number of charge carriers times the charge on those carriers, times their speed, times the cross-sectional area of whatever that current is moving through. So then we can derive, finally, this equation, maybe an easier way to use it for the magnetic force acting on our current carrying conductor, and that's equal to the magnetic field that conductor is experiencing times the current running through it times the length of that object times sine theta, where again angle theta is the angle between the magnetic field and the direction of our current. So let's calculate the magnetic force on a current carrying wire in Earth's magnetic field. And what we're eventually going to do is compare this magnetic force with the gravitational force on the wire so we can see the difference. So here we have a wire. It's oriented from in the east-west direction here, and it's carrying a current of 22 amperes. And at this location, we're going to assume that the magnetic field of the Earth is directed from north to south, and that it has a magnitude of 0.5 times 10 to the minus 4 Tesla. So the Earth's magnetic field is on average about this value here. Okay. And so we're going to calculate the magnetic force on this current carrying wire due to the Earth's magnetic field. And so here we have that our direction of our current is perpendicular to our magnetic field. And so our magnetic force is equal to the magnetic field times the current times the length of our wire times sine theta. Okay, remember that theta is the angle between the direction of our current and the magnetic field. But here in this setup, that angle is 90 degrees, so sine of 90 degrees will be 1. Okay, and so then our magnetic field of our Earth is 0.5 times 10 to the minus 4 Tesla, and we have our current is 22 amperes. And I forgot to tell you that the length of our wire is 36 meters. Okay, so L is 36 meters. So that will go here, 36 meters. We multiply all that together and we find that the magnetic force is 3.96 times 10 to the minus 2 newtons. Okay, so I've moved my magnetic force up here so I have more room. Now we're going to calculate the gravitational force acting on this wire. Okay, so our gravitational force in this case is just going to be equal to the mass of our wire times g, the acceleration due to gravity. But we don't know what the mass of the wire is yet, but we can find it. And so we're going to assume that this wire is made out of copper, and I know its cross-sectional area. So remember that the density of a material is equal to its mass divided by its volume. So the mass is equal to its density times its volume. So the mass is going to equal the density of our copper, and the density of copper is 8.92 times 10 to the 3 kilograms per meter cubed. Okay, and then our volume here. So a volume, we were thinking about the volume of a cylinder, or the volume of our wire, which we can approximate as a cylinder. The volume of that is going to be its cross-sectional area times its length. So we're going to multiply this by the cross-sectional area of our wire, which happens to be 2.5 times 10 to the minus 6 meters squared, and then times its length, 36 meters. So we find that the mass of this wire is 0.803 kilograms. Okay, so the gravitational force is going to be this mass, 0.803 kilograms times g, the acceleration due to gravity, 9.8 meters per second squared. So if I take this mass times g, I find that the gravitational force is 7.87 newtons. And so if I divide FB over FG, I find, oh actually let's do it the other way since FG is bigger. We just want to see what the ratio of these two are so we can better understand them and better compare them. So if I take the ratio of FG over FB, so take 7.87 newtons divided by 3.96 times 10 to the minus 2 newtons, I find that that ratio is about 199. So in this situation, our gravitational force acting on this wire is almost 200 times larger than the magnetic force acting on this wire due to the Earth's magnetic field.